Good afternoon and warm welcome to all. Let me introduce GN Khalsa College first. It was established in the year 1937, including more than 40 departments, accommodating more than 7,500 students. Moving to highlights of the college is accredited with A grade by NAC with a CGPA of 3.54. It is awarded college with potential for excellence by UGC. Also, Star College status by DBT, FIST grant by DST. Khalsa College is recognized as CIRO, Scientific and Industrial Research Organization, declared as a Best College Award in Urban Area by University of Mumbai for the academic year 2011 and 12. Khalsa College runs many innovative courses. One of them is 5 years integrated course in bioanalytical sciences, FYIC. The course started in the year 2010. The curriculum is designed to cater to the requirements of academic, research, and industries. It helps to imbibe research culture right from UG level. To celebrate the 10th year of such an innovative course, the department has organized a series of lectures, which includes today's LCMS hyphenated techniques as a fourth in the row. With this, I call upon my colleague Ms. Priyankal Sharma to introduce today's resource personality, Dr. Ajit Datar.
Hello, good afternoon, all. Thank you, Maria ma'am. I, Priyanka Sharma, on behalf of FIIC, welcome you all in today's session, Hyphenated Technique LCMS. Our main agenda to organize this webinar is to provide essential information and theoretical understanding on liquid chromatography and mass spectrometry. And I'm extremely pleasured and honored to introduce our guest speaker, Dr. Ajit Ganesh Datar. He is currently a part of Shimadzu Analytical Indian Private Limited, where his main job profile is to provide instrumental analysis support and training. Because of his interest in teaching, he is currently adjunct professor in Khalsa College and also in many several colleges in Mumbai. Let now get a closer look to his education. Dr. Datar pursued his MSc degree in 1971. In same year, he was a recipient in Department of Atomic Energy Fellowship in 1971. He carried out his PhD research from Analytical Chemistry Division of BARC and obtained his PhD in 1976. Now, let me take you to his past experience and achievements. Prior to Shimadzu, he was with Thermo Electron as general manager, responsible for promoting advanced mass spectrometry products of Thermo Finnegan. He served for Chromline and IR Technology as technical director and senior manager, respectively, for periods of 15 years. His first assignment was with Central Research Station of Associate Cement Limited as a research officer, and he served ACC for 12 years. He also developed methods for characterization of catalyst and process product using catalyst. He indigenously developed BET surface analyzer and particle size analyzer. After knowing about his experience and vast knowledge, I would request Sir to take over the forum and enlighten us with his powerful power of knowledge. And I request please take over it. Hello, sir.
Yes. Yes. Thank you. Thank you, madam, for your kind words, and thanks all of you for giving me this opportunity to talk to all these great people who have come for this particular training on our seminar on hyphenated technique, LCMS. This is a technique which I love most, and that is why I thought I should talk about this technique to all of you. Well, those who had attended my previous talk, they know my friend very well and with what objects he's playing with. He's playing with some 5 objects. And who is he? He's nothing but analytical chemist like me. And he's playing with sensitivity, selectivity, separation, structure, and speed. These I consider as 5 important S of analytical chemistry. Each term is very important, and I explained last time each one of these terms, but still I will just go quickly because there could be few who are new to this particular lecture. Those who have attended, it could be sort of a little repetition to them. Sensitivity, we always know, we always talk about analytical instrument being sensitive. We talk about selectivity of analytical instrument when we can measure something selectively over others which are present in your sample. So whether we can select something very selectively in a difficult matrix. If that is difficult, then we need to carry out some kind of a separation, and separation could be anything, right from liquid-liquid extraction, solid phase extraction, or solid phase micro extraction, or it could be as simple as filtration or precipitation, etc. And of course, the best technique for separation is chromatography, and that is why we talk about chromatography being used with mass spectrometry. Structure is very important. So whenever we work with any organic molecule, we like to know what it is, and also many times how much it is. So what it is given by the structure of that organic compound, and we need to measure it many times. So drug discovery, we would like to know what we are trying to make. If there is an impurity in a drug, we need to know what it is, whether it is toxic, non-toxic. So many places we need to find out the structure of organic compound. And then all these kind of measurements, especially when it is an industry, we have to do it as fast as possible. The speed of analysis is very important. How fast I can submit my report, how fast I can do the analysis, how many samples I can analyze per hour, how many elements I can measure in a given sample in a given time. So all such things are the ones where we talk about the speed of analysis. While playing with these 5 objects, one has to reduce some errors, and those errors are sampling error. Sampling error, according to me, is there are 2 parts involved in it: whether your sample represents the bulk or not, so you have done proper sampling or not. And second thing is whether you have prepared your sample properly. If you are doing extraction, whether extraction is complete, whether you have extracted the analyte from the given matrix properly or not. So sampling error can happen there. So error can happen there. So sample preparation, sample collection, sample storage, all those aspects will be there, and as much care as you take here, your sampling errors will definitely decrease. Then there is always a background associated with whatever analysis you do, and this background could be because of the matrix, and then the matrix adds to the background, and because of which your signal of the analyte gets affected. So you have to reduce your background, and that can be improved by proper sample preparation. Many times your solvent which you are using as a mobile phase or for preparation could add to the background, because if it is not very pure, so you have to make sure that you use right reagents, right solvents, and then take all the precautions to remove the interference or background which is coming from your sample matrix. Noise is the third thing which one has to reduce. Noise is inherent part of any instrument, and you always talk about signal to noise ratio when you try to find out the sensitivity, and signal to noise ratio has to be good. So if you want to detect something, signal to noise ratio has to be 3:1. If you want to quantitate something, signal to noise ratio has to be 10 or more than 10. So these are the limitations. So we talk about LOD and LOQ, and for LOD and LOQ, we always talk about signal to noise ratio. So these terms are very important, and if you can manage to play with these 5S, then you have to suppress those errors, then only you will be able to get better results. And why I'm talking about this particular way is only to again emphasize that when we look at the instrument like GCMS or LCMS, structure is very important. Many other instruments will not give you structural elucidation, but mass spectrometer gives you structural elucidation also. And then in addition to that, it improves on sensitivity, it improves the selectivity, it improves the separation capability, because chromatography does separation, mass also does the separation. Mass analyzer also does the additional separation. You get structural information, and you can even increase the speed of analysis because of the mass spectrometer attached to it. And how it is done, we'll see sometime later. So the all the 5S are possible to be given by MS, and that is why we are talking about MS. I last time explained you some of the hyphenated techniques, and out of these hyphenated techniques, we are going to talk about GCMS, LCMS, and MSMS. GCMS I have covered last time, and then there will be some few slides I will be repeating, because to get into LCMS, I require something before that to be talked about. Then it would be possible for me to enter into LCMS. So I will talk about a little bit about GCMS. This slide I showed you last time, where chromatography only gives you one single dimension, that is retention time. And on the basis of retention time of a standard and retention time of your unknown compound in your sample, if both of them match, you can say this probably is the compound which is present. But then there could be many compounds which could have exactly same retention time. So you'll have to use a cautious sentence that this compound may be present. Mass spectrometer gives you one more dimension. It gives you molecular weight. So if now both the things match, the standard molecular weight and your sample molecular weight matches, both of them elute at the same retention time, that means you have more confidence in saying that the sample with this. It is still not perfect, but when I get a third dimension, when I get a spectra of that particular molecule, that means it is broken into pieces and forms of fragments, and the fragments also are shown in the spectra. We call it as a mass spectra. And if that mass spectra matches with that of a standard, retention time is matching, molecular weight is matching, spectra is matching, then you have more confidence in saying that this compound could be present. So that is what we did last time. We talked about the components of a mass spectrometer. I mentioned to you about the types of ionization, volatile and non-volatile. And volatile samples can be measured by GC. Non-volatiles, generally we, of course, go for LC. There is another way you can ionize the sample you can convert the non-volatiles by derivatization to volatile, and then you can analyze them by GC again. Now for GC, and when your sample is volatile, you have two methods of ionization, EI and CI. So last time we covered those, and then we talked about the GCMS. So today we'll just talk about them again, and then we'll enter into the non-volatile area, which is the talk of today. So I will not describe that part, that is going to come as we progress. So we talked about electron ionization, we talked about chemical ionization. We said that electron ionization it is an energetic process. We are bombarding molecule with a 70 electron volts. So the molecule is already in a vapor phase. It comes out from the column. It goes to the ionization chamber. You bombard that with electron, and then the electron will break that molecule. It may produce a molecular ion. It will give you a lot of fragments, and those fragments those fragments will be able to give you structure of that molecule. There is some thing which can happen also. If the molecule is very fragile, you may not get a molecular ion, so you may miss the molecular weight information. Whatever it is, you have a library spectra, because the spectra obtained by this process is always same, because we are using the 70 electron volts as the energy of electrons, and when you use that, the spectra are always reproducible. So whatever compound I do today, if I do it tomorrow, or if I do it after a year, or if I do it on somebody else's machine, I'll get the same spectra every time. And that is why that spectra can be stored in the library. And there are two commercial libraries available, NIST and Willy, and they have more than 3 lakhs of organic compounds, and their spectra stored in that. And that helps in identification of the compound. So this is how electron ionization works. I will quickly go through. This is the filament, rhenium filament. When you pass a current through that, the electrons are produced, they go towards the anode, and then you get a sample from your GC column. It gets ionized, and these ions are pushed through the lensing system into mass analyzer, which is on this side. So that is how the ionization, electron ionization works. Then we talked about how the molecule can get fragmented. So ABC, if some molecule is there, arbitrary molecule, it can give you so many fragments. It can give you ABC, AB, BC, AC, all these are plus, so ions, and each one of it has got its own molecular weight, or and then using that we can find out how the ABC is made. Okay, so that is how you can find out from this the structure of this. In addition to that, I mean, you can use your own logic to find out what is ABC plus, or in addition to that, you have a library which can help you in finding out the structure of this compound. So there are two ways possible. If one way is where you know how to derive the structure from the spectra, you can do it yourself also. This is one spectra which I showed you last time. It is a spectra of acetophenone with a molecular weight of 120, and you can consider this as A, this as B, CO group, and CH3 as C group. So this is ABC. And when you look at the spectra of this compound, it gives you spectra like that. So if you calculate the molecular weight, it is 120. We are getting a peak at 120 mass. This is M by Z, mass to charge ratio, and this is relative abundance or relative intensity. What is done is that whenever whatever signal you get in number of counts, those counts are measured, and the one which gives you maximum count is considered to be 100. And with respect to that, all other counts, whatever this ion is giving, this ion is giving, this ion is giving, that is converted into percentage. And then this graph is plotted. So this is called as relative intensity or relative abundance versus the mass. So for this mass 105, it is the most stable ion. It has it is considered to be 100% on the basis of whatever I just talked about. And with respect to that, the intensities of others is calculated in the percentage. So when you have acetophenone, it will always come like that. With respect to 105 will be the base peak, 120 will be always somewhere around 40%, 77 mass will be somewhere close to about 85%, and this 43 could be close to 20%. So this will be always constant. The spectra would always look like that. So when I see a spectra like that, and when I get into the library, it will tell me that this compound is nothing but acetophenone. And that is how all the spectra, whatever you have, they will come like that, and they can be referred to the library. And then you can also analyze them with yourself because 120 to 105, the difference between these two is 15. So there is a 15 here. So C is 15, that is lost. 105 to 77, the loss is 28. So C double bond O group is at 28. And this 77 must be this phenyl group, C6H5. So you are getting that. And 43 could be COCH3. So this forms an ion. So you can consider it as BC plus, A neutral, A, this is A plus, BC neutral, ABC, AB plus, which is 105, C neutral. So like that, when you look at that previous equations which I showed you how ABC fragments, here you are seeing the same thing almost happening as far as the structure of this compound is concerned. And that helps you really to find out the structure of this compound. Ni is still a library which has been used here. Okay. Well, I come to the advantages and limitations of GCMS. So that's one thing, and that is how I'm going to enter into LCMS. So we know advantages of GCMS are something which are quite good. Capillary GC has the best separation efficiency. So GC generally, when we use along with MS, it is always a capillary gas chromatograph. To use a capillary column in a GC and then use it along with mass spectrometer. And capillary column has the highest separation efficiency. It can separate even 100 compounds in a given mixture. So that kind of a capacity or capability is not there with LC column. So in that respect, GC has a great advantage that it can do separation by itself to a large number of components in a sample. It is simple compared to LCMS. It is sensitive and selective method of analysis. So it is in fact more sensitive than LC, for the reason that when we use a capillary column, it is an open tubular column. So there is some factor which we call as Adie's diffusion when we define Van Dimter's equation, that Adie's diffusion A is not there, and because of that the value of H, HETP or height of plate is small, that means number of plates will be higher, and that is how efficiency of capillary column is always high. Then it is a library searchable spectra, which I talked about. With 70 electron volts, we get a spectra which can be searched in the library, and you get a good indication about what is in your sample. It is having less interference, because what you are doing is you are making the compound volatile, and then the volatiles only are going through your GC column. If your sample has some biological matrix, you can easily extract the volatiles without much of an interference, and then they can be studied very easily. So it generally gives less interference compared to LCMS. Limitations, major limitation is that there are only about less than 10% of the organic compounds which are volatile. And because of that, it has its own limitation that we cannot analyze those compounds which are non-volatiles. So this was one of the major limitations of that, because 90% of the compounds which are non-volatiles, or more than 90% of the compounds which are non-volatiles, cannot be studied by GCMS. Molecular weight is maximum about 1000 or 1100 Daltons or 1100 AMU. So you cannot increase the molecular weight beyond that. And there are lots of organic compounds, peptides, protein, carbohydrates. They have molecular weights much more than 1000. So they cannot be analyzed. 90% of the organic biological samples are non-volatiles, which I already talked about. And then another, which is not very critical, but then compared to GCMS, LCMS has one advantage, that most of the detectors which are used in LC are non-destructive detector, and most of the detectors which are used in GC are destructive detectors. They are all flame detectors, flame ionization detector, flame photometric detector, nitrogen phosphorus selective detectors. All these are the flame-based detectors, and because of that, you cannot have one detector connected to MS directly. You have to split the sample. While in case of LCMS, you can connect UV or fluorescence or any other detector, refractive index detector can be connected to mass spectrometer, because sample doesn't decompose. From this detector, it goes to mass analyzer. So that is one advantage of LCMS, and that is the disadvantage for GCMS. And that is why we say that hence we require LCMS for all such disadvantages or limitations of GCMS. Fine. So we talked about the history of LCMS and GC. We can see GC got developed somewhere in 1952, and immediately within 5 years, GCMS came into existence. LC was developed by Mikhail Svet in 1903. MS was developed by J.J. Thomson in 1905. So both the techniques almost started together, but they could not meet each other for a very long time. People tried a lot of things in between. After 65, when first HPLC instrument was developed by Waters, people tried to have a combination of LC and MS, because they could see GCMS was very successful, and they wanted to have badly LC connected to MS, but then they miserably failed. Only after somewhere around 2000 or around 2000 year, LCMS was really used in a better way. Till that time, people tried a lot of things but were not very happy. Okay, so a lot of things were discontinued in between that period. Okay, so the LCMS really happened a little late. I consider all these are LCOS or G2MS. I consider them hyphenated techniques as marriage of convenience. So we can say that the marriage between LC and MS happened little late, so at the old age. And if we can say old age marriages are successful, LCMS marriage is definitely successful. Okay, let us go ahead and talk about that more, and why it was difficult to have LCMS at one time and why it is easy now. So why can't we use EI and CI all the time? So we use electron ionization and chemical ionization for GCMS. Why can't we use that? The reason is that both these techniques are gas phase ionization techniques. That means you have to take your sample into gaseous phase. There is one good thing, there is a limitation of a mass spectrometer also, that mass spectrometer would like to have sample in form of ions. That is one condition. And then there is another condition which is very essential, that the sample has to be in a vapor phase. So these are two conditions which are very essential for the sample to be in the vapor form. And in case of EIC, you do the ionization in the gas phase, that means you want to have sample also in a gas phase. Well, small volatile molecules are simply heated and they enter into gas phase. So it is very easy for GCMS to work, because generally we analyze molecules below 500 or below 600 molecular weight, and those can be easily converted into volatile gases or vapors, and then they can be easily analyzed by the mass analyzer, because it gets the sample ionized, it gets the sample in vapor form, and it has to separate that. It is very difficult to get large or involatile molecules into the gas phase. If you heat them, degrade. So heating them just degrades the molecules, or it can even spoil your instrument. So it is very difficult to have involatiles which can be analyzed by mass analyzer. So we require some different ionization techniques if we really want to take the non-volatiles into mass analyzer. So people tried a lot of things. They came out with some solution. So it was a challenge. Involatiles a real challenge for MS. It was a difficult task, and research concentrated on this task for some time, producing a variety of innovative techniques, now mostly superseded. So people talk about field desorption ionization, fast atom bombardment, secondary ion mass spectrometry, thermospray, particle beam, moving bell technology. There are a lot of them. Okay, so all these techniques which were developed for possibility of combining LC to MS, people were feeling a need of that. They were drastically interested in having this kind of a combination, because GCMS was really successful. It was getting popularity at that time, but LCMS was not possible. So they were really disturbed because of that, because they were knowing that 90% of the compounds are to be analyzed and LCMS is not possible. So they tried a lot of things. It became useless after some time. And then I thought of drawing a cartoon for indicating why LCMS is difficult. Okay, this love affair is impossible because one is in water or a liquid media, other is in a gas media. And that's the main problem with non-volatiles. Non-volatiles are in the liquid media. They require solvent to be there, and they cannot be taken into vapor phase, because if you try to take them into vapor phase, they will decompose. Mass spectrometer works in a vapor phase. So if mass spectrometer wants your sample in a vapor phase and sample is non-volatile or thermally labile, how to take that sample into vapor phase and then push it into mass analyzer? And that was a real challenge. And that is why it was thought that this kind of love affair would be impossible. There is one more main reason also, another reason also, that LC mobile phase generates too much amount of gas to be handled by vacuum system. Now imagine, generally when we use HPLC, we use 1 ml per minute of a flow of a mobile phase. When we use GC, we use 1 ml per minute flow of a carrier gas like helium. Now both of them, GCMS as well as if we use LC, we use 1 ml per minute flow. Both these 1 ml are different, because in one case, it is already in a gas. Okay, so 1 ml of a gas is moving through the column in case of GCMS. While here, we have a 1 ml of a liquid which is moving through the column. And when it gets converted into gas, how much gas it would generate? Let us do some simple calculation, which I will do. Otherwise, I generally put these questions to my students to do the calculation. If I have 1 ml of water, because water is one of the mobile phase when we use reverse phase chromatography. So if we have 1 ml of a water, and if it is flowing through the column, and if it comes out and we have evaporated it to push it into mass analyzer, how much amount of gas it would generate? So we can use Avogadro's hypothesis. We know that 1 gram mole of a substance would generate 22.4 liters of a gas at NTP. Now we have 1 ml of water. That means we have to convert this 1 ml of water into gram moles. We know that molecular weight of water is 18. So 18 grams of water would generate 22.4 liters of a gas. So how much 1 ml would generate? You know, water density is 1. So 1 ml is 1 gram. So 18 grams generate 20.4 liters of gas. 1 gram of water generate 22.4 divided by 18, and that comes to 1.2 liters of a gas. Now compare it with 1 ml per minute flow of a GC gas and compare that with LC gas, when it enters, because the mobile phase converted into gas will generate 1.2 liters of a gas, that is 1200 times more the gas which gets into the vacuum system of a mass analyzer, and it will collapse. Vacuum system will collapse with 1200 ml entering into it. In case of a GC, we did not allow pack column because it was not able to take even 20 ml of a gas, and that is why we had to move from the jet separator to the interface, which is very simple, and we have to move from pack column to capillary column in case of a GCMS. Here we are talking about 1200 ml of a gas which enters into vacuum system, and here it will definitely spoil the vacuum system because we are using polar solvents like water and methanol and all these kind of solvents, and they are, especially water has leaching property. Once it gets into vacuum, it will deposit it there, and it will be very difficult to take it out from the vacuum system. Though what is it for us? It is oil for system, so not use that. Okay, so sample enters into the mass analyzer, it will definitely create problem. But then people try, though they were knowing that it is a challenge, they tried all those which I just listed. Those methods become historical, and now we have some modern methods which are called as electrospray, atmospheric pressure chemical ionization, matrix assisted laser desorption ionization, which is used for non-volatiles. It is never connected to LC, but I just still listed it there. And there is one more technique which is called as atmospheric pressure photoionization. So let us look at some of the old techniques to just understand what was happening. This is the moving bed. So the LC column, the mobile phase comes here and drops on this bed. This is the bed which is moving like this. Okay. So it moves like this. There is a fan which will try to evaporate the volatile mobile. It goes further, comes here, comes here, comes here. There is a heater here which will evaporate everything. And what I have not shown is from here, there is an EI filament which will bombard the electrons onto the sample, which gets evaporated here, and then it enters into the mass analyzer which is on this side. Now remember one thing, that when I'm putting it, this is all connected to vacuum system. So there are vacuum pumps here. Now we have just now seen that 1 ml of a liquid will generate 1 liter of a gas. Now if that happens, how to get rid of all that gas? A lot of gas molecules, vapor molecules of your solvent will also enter into MS, because with electron ionization, some of them also will get ionized. They will also enter into mass analyzer, will give you huge background. And what my juggler says, we don't want a background. So it doesn't help. So this technique will not help. They tried a thermospray, which was useful for some time. It was a commercially available interface between LC and MS. So they used normal LCMS LC flow rate 1.5 to 1.5. It was good for some semipolar compounds. I will not call them very polar compounds, semipolar compounds. It generally produces M plus H ion, so proton gets added to the molecule, or sometimes ammonium gets added to the molecule, because many times ammonium acetate is used as a buffer. Then what we do here, we heat HPLC eluent to dissolve it, analyte, so remove the solvent. And then again, because of the heat applied, there could be problem with thermally labile compounds. So anyway, those compounds are not possible to be analyzed. It can block because we are nebulizing a flow of your mobile phase through a capillary, and that capillary can get blocked. And of course, it is not commercially available today. Let us see how it works in a short. I will only explain the first part of it. This is the almost same thing. So HPLC flow comes, it is nebulized. So you are forming a spray of mobile phase along with a lot of droplets here. Everything evaporates here, and then you have an EI filament here. That EI filament will ionize the vapors which are getting generated, and then the vapors or the ionized molecules in a vapor form will get into mass analyzer, and it assumes that most of the mobile phase will go in this direction and get out, which doesn't happen, and you will get again a huge background of mobile phase into mass analyzer, and that can create a problem. There was another one which was developed, was particle beam interface. So here the mobile phase is nebulized with helium instead of nitrogen. Earlier case it was nitrogen. It is sprayed into a large volume here, and then it enters through the two jets. Okay, so there is a jet, and in this side between the two jets there is a vacuum connected here. So what is said is that as the mobile phase gets evaporated here, it enters through the jet. As mobile phase is a lighter molecule in terms of its size and molecular weight, it diffuses into this area and gets sucked by the vacuum system. While the heavier molecule of your sample will not get diffused in this direction, they will go straight, and there is the EI filament which will bombard and then produce the ions. But remember that the entire mobile phase doesn't get evaporated. Some of it also will enter here and can create a problem. So this particle beam interface and the thermospray both were available commercially. So they were having some lifespan where they were used by the scientists for their work on LCMS. But when the new methods got developed, this became useless again. Then we talked about one more method which is called as fast atom bombardment. This was the method which was introduced, and it was the first method which was good for the biological sample. So people could analyze some sugars, some lipids, some steroids by using this technique. And the technique was something like this: that you had a matrix which is glycerol or glycol. On the matrix you put your sample and bombard this matrix with the atom gun, fast atoms. And because of the energy of the fast atoms, the matrix will evaporate. As it evaporates, the sample which is dissolved in the matrix also will get into the molecules which are evaporated. It also gets into vapor phase, and then the ions get formed as the matrix give the protons to the molecule of interest, and it gets ionized, and those ions enter into mass analyzer. This is how it works. So you have a green are the matrix molecule, glycerol or glycol. The gray ones are your sample molecules, as I said, peptides. And then you have a gun of xenon, a fast atom gun of xenon, which hits here. It produces molecules which are volatile, glycerol or glycol. Along with that, some molecules of our interest are also vaporized, and then the charge get transferred to the molecule of interest, and they enter into the mass analyzer, which is on this side. Of course, what is not shown here is even these green molecules of your matrix will also enter here, and that can give you huge background. It has some advantage because so far GCMS and LCMS both were not able to, so far at that time, they were not able to go above 1000 Daltons. So 1000, only molecular weights up to 1000 molecular weight, those compounds were possible to be analyzed. While here, because of the fab, it was possible to go up to 7000 Daltons. So small peptide molecules could be analyzed by that. And that was one of the great advantage of this technique. And it was the first ionization technique which was tried by the biological scientist. It was able to give fast analysis. So directly you put the sample onto the matrix, bombard with xenon, and you get the spectra. It is a soft ionization, so you get only molecular ion. The molecular weight is obtained, you don't get fragments. It is less sensitive, again because of the background which comes. Little fragmentation, so less structural information. It gives high background because of the matrix. One important thing is that you require solubility of sample in matrix. So your sample has to be soluble in glycerol or glycol. Your low utility for non-polar type of samples because the matrix which is used is polar. So non-polar will not dissolve in that, and it is difficult to couple to LC. And people tried that, and we will see how it was done. So you have a continuous flow path which is possible to be connected to LC. So your LC flow comes like this. It enters into this area. Now there is some kind of a porous material here on which the glycerol or glycol is used. And then the LC mobile phase comes here, and it percolates through the pores from here onto the surface here. of the matrix, and then you have a xenon atom bombardment onto that. It will get ionized and then it will enter into mass analyzer. So LC flow comes, get diffused into the matrix and gets analyzed. Now the problem with that is that when your LC mobile phase comes, it will also dissolve your matrix, because the mobile phase also being polar, sample being polar, and everything being polar, the mobile phase will dissolve the matrix, and then you every time you have to replenish the matrix. You have to remove that, put a new matrix, and again try the next experiment. And that was problematic. And again, it was not able to give you good intensity, good sensitivity. So it was again not a very successful technique. We'll just talk about this matrix assisted laser desorption ionization MALDI, because this was again a very successful technique for non-volatiles, though it has a drawback that it cannot be coupled to LC. But we should know what this technique is. It is similar process to FAB. That means we require a matrix. Now the glycerol or glycol are not the matrix here. We use synapic acid or cinnamonic acid as a matrix. These are benzoic acid derivatives. They are crystalline compound. They are used as a matrix, on which we bombard a laser beam. I think the wavelength of laser beam is 337 nanometer, and then it is this MALDI is coupled to time of flight mass analyzer, because time of flight mass analyzer has a mass range which is much higher, and the sample is mixed with the matrix on target, where your sample and the matrix sit together. It will have intense matrix ions, so they will also get into your mass spectra. And preparing sample onto a target is an art, or was an art earlier, but now it is no more an art, because there are a lot of auto samplers which are working. So putting the sample onto the matrix like cinnamic acid or synapenic acid is not a problem now. This is the person who invented it, Koichi Tanaka. He invented the MALDI as an ion source. He is working with Shimadzu, where I am working, and he is in Japan and heading our mass spectrometry division there. And he received a Nobel Prize in 2002 for development of a MALDI as ion source. And what happened because of that? Now we were talking about FAB, which could do only 5,000 molecular weight or 7,000 molecular weight, but by invention of a MALDI, people can analyze proteins up to even 500,000 Daltons, 5 lakh molecular weight, or people are going even up to 2 million Dalton molecular weight because of the MALDI as an source. And it is very fast. It can do about 1,000 samples per hour. This is the kind of a spectra you get. So this is the albumin protein, bovine serum albumin protein, with a molecular weight of 66,000. So at one moment, nobody thought that such a high molecular weight compound can be vaporized, ionized, and can be analyzed by mass spectrometer. So for a very long time, nobody even were able to dream that this is possible. Okay, so now it has become very possible, and the growth of biotechnology which has happened is because of this development, and then we are going to see some more development which has happened. So because of that, the biotechnology has developed to that extent. Well, now we come to methods of atmospheric pressure ionization techniques, which had changed the LCMS totally. Okay, so we'll have a look at these techniques. Well, electrospray is the first technique, and this is developed by scientist called John Fenn, and another person is Dr. Mann. So both of them developed this electrospray ionization, and he also received a Nobel Prize in the same year along with Koichi Tanaka. So both of them received the Nobel Prize. So that is why I said joint Nobel Prize were awarded to these two scientists. One is John Fenn, other is Koichi Tanaka, and both of them received a Nobel Prize for almost same cause, that they could take non-volatile, high molecular weight compounds into the mass analyzer, which could separate them. So nobody could have dreamed that anything above 5,000 Daltons could be analyzed by a mass spectrometer. But here they could show that the molecular weight of even more than a lakh of the molecular weight more than 100,000 can be analyzed by using these techniques. And what they really did was they provided wings to the elephant, so that elephant could fly into the mass analyzer. Well, these are the three people who are responsible for this. Koichi Tanaka, Koichi Tanaka, Dr. John Fenn, and Dr. Mann. So they are sitting for receiving their Nobel Prizes, and they're watching the function as it goes on. Okay, so we come to the techniques which are called as atmospheric pressure ionization techniques. It is most important LCMS technique, most important LCMS interface and ionization. There are three types of API. Here API is atmospheric pressure ionization. One is electrospray. Other one is called as atmospheric pressure chemical ionization. Third one is called as atmospheric pressure photoionization. And all new LCMS use API as a source. API means any one of these three atmospheric pressure ionization technique. What is important here? Ionization takes place outside the vacuum region. So it is taking place in the atmospheric pressure. And that has really made the change. The atmospheric pressure has made the change. So as the ionization doesn't take place in vacuum, it has changed the concept of the LCMS totally. So this is what is the electrospray ionization. We have a capillary through which the mobile phase is passing. This is a metal capillary, and what is done is, and this is atmospheric pressure. So with the help of nitrogen gas, the nebulization has happened, the spray of mobile phase has come out, and then to this capillary, there is a high voltage which is applied. Something like 4 to 8 kilovolts of voltage is applied to this capillary. And because of this high voltage, positive high voltage which is applied, the droplets which come out, they are charged droplets. There will be positive charges sitting on the droplet depending upon the area of the drop. So these positive charges which are sitting on the droplets, because we are using, of course, polar solvents, river phase chromatography is always followed. We have a river phase mobile phases, and they get charge sitting on the surface of those drops. And then there is some heat provided here. There is a flow of nitrogen gas in this area because it has to be inert area. So as nitrogen gas flows here and whatever heat is applied here, the droplet starts evaporating. As the droplets evaporate and shrink in size, what would happen? The charges sitting on the droplets, they cannot go out. They will start shrinking. So they will also come closer to each other. As all those positive charges sitting on the drop starts coming closer together, what will happen? They will start repelling each other. So electrostatic repulsive forces will start acting, and these charges sitting on the drop will start repelling each other. There is one more force acting on the drop, which is called a surface tension force, which will try to keep the drop intact. So the process continues. As the drop shrinks further, what will happen? The repulsive forces, repulsive Coulombic forces, because of these positive charges want to go away from each other, they become more stronger than the surface tension force which is acting on the drop, which resists the breaking of the drop. But then at some limit, which is called as Rayleigh limit, the droplets shatter into pieces, and then surface area increases. The charge gets divided. The process continues till all the droplets break. And if it is just a solvent, it will go out. But if any of the droplet has a molecule inside, because molecule is in very small concentration, so entire mobile phase will have very small number of molecules sitting inside, but molecule will be never alone. It will be solid molecule. So the drop will be there. So other solvents will be covering the molecule which is sitting inside. And as the droplets evaporate and shatter and go out, the charge finally comes onto the molecule. There is nothing to hold him. So it has already come into vapor phase, and then it enters into the mass analyzer. And that is how we get rid of most of the mobile phase because of the flow of nitrogen gas. Some amount of nitrogen may come inside, but the vacuum system of mass analyzer, there is the roughing pump or rotary pump which is pushing which is connected here to have a good vacuum of -3, and then there is a turbomolecular pump here in this region which will bring the vacuum level of -5. So this is what is happening here. So spraying nozzle, you get positive charges sitting on the droplet, and as the droplet shrinks, the positive charges repel each other. at the relic limit, it will break down, what we call Coulombic fission occurs, and finally the molecule with little mobile phase which is covering here, that also breaks, and you get molecule with a positive charge that enters into the mass analyzer. Okay, that is how the whole electrospray ionization process takes place. And as I showed you, the ions and gas plus ions are formed here. They enter, this is 1 torr in the first region, 10 raised to minus 3 torr in the second region, and 10 raised to minus 5 or minus 6 torr in the third region. And that is why the mass analyzer region, we get desired vacuum, we get desired ions now without any kind of background coming from my sample or solvent, especially solvent, and I get a much cleaner molecules which come inside, and then the sensitivity of femtogram level or picogram level can be easily achieved because of that. So electrospray has many other names. It is called as ion spray, nano spray, sonic spray, pure electrospray, and it is termed as ESI, ES or IS. Okay, so these are funny names. Nano spray is something different. Nano spray is the one where we used a nanoliter flow rate, so not milliliter or microliter flow rate. Very, very small flow rate is applied, and then it can analyze the sample, and this is very essential when we analyze the biomolecules, especially proteins or peptides which come out from a single cell. So we have very, very small amount of sample which needs to be analyzed. We use a nano electrospray. Okay, this nano spray, nano electrospray. So this is the theory, as I already explained, that droplet shrinks and the Coulombic forces become more stronger than the surface tension forces, and it shatters to give you molecules. So this is one theory which is called a charge residue model, which I just explained. There is one more theory which is proposed, which is called as ion evaporation model. So in this model, what happens? As the droplet shrinks in size, one ion from the surface evaporates and goes out. As it shrinks further, one more ion will evaporate and go out. So this is called as ion evaporation model. Okay, so both the models are probably working, so that finally what is important is you get the ion free from the solvent, and then it is already in a vapor phase, gets into mass analyzer, gives you desired information. And that is what this ESI can do you, and that is what John Fenn could develop a best technique for connecting LC to MS. Electrospray, ion ejected from solution to gas phase, can produce multiply charged ions. So this has to be remembered, multiply charged ions, because many times the molecules which you are analyzing, they are having a higher molecular weight. They could have a lot of groups which can attract protons. So proton affinity groups would be more on the surface, on the molecule, and that is why not only one proton from the solvent will be transferred to the molecule, there could be multiple protons which can get transferred to the molecule. So here generally what we see is a protonated molecule or multiply protonated molecule, and if there are multiple protons added to the molecule, the Z will not be 1, Z could be 2, 3, 4, 5, anything. Okay, so M by Z would be different because of that. Generally in case of GCMS, Z is always equal to 1, so we never get more than one electron ejected out, while here the proton is added, so number of protons added could be more, so there could be multiple charge, which is very much possible here, and M by Z could be different. Now it means that if on a molecule if you have something okay, if on a molecule, if there are 5 charges onto the molecule, and if the molecular weight is 1000, and if it has 5 charges, so M by Z will come to be 1000 by 5 will be 200. So you will get that molecule at 200 mass. Okay, so multiple charging will reduce the presence of that peak on that M by Z axis. So instead of coming at 1000, though the molecular weight is 1000, it will appear at 200 mass because there are 5 charges on it. So remember this. It is the softest ionization technique. electrospray is the softest ionization technique. In fact, all these electrospray, atmospheric pressure, chemical ionization, all these techniques are soft ionization technique. What does it mean? They give you molecular ion. They do not give you fragments. Okay. So what to do with that? So we'll see that. It is not very tolerant of salts. So we have to use always salts which are volatile. So we have to use only ammonium acetate, ammonium formate, and these kind of buffers. We cannot use what we call as phosphate buffers, okay, which are generally used in LC, normal LC. But if we have a LC method with phosphate buffer, we need to change that method to volatile buffers like ammonium acetate, formate, etc. So that is what is necessary, because the MS doesn't tolerate the salts. If salts get deposited in the inside pores, that will spoil your MS, and MS is the most costliest part in the entire system. It produces adduct ions. Again, this is because, as I said, the molecules are highly polar. They have non-volatiles and highly polar compounds. And with that kind of a polarity, they can attract any other group, and that group can get added to that. So many times we have this kind of molecules. They can attract even water, and water can be adduct on that. They can attract ammonium, and ammonium adduct could be there on that. They could even attract acetonitrile as a molecule, and you can have acetonitrile adduct onto the molecule. So these kind of adduct ion formation is quite common in case of electrospray ionization, and because of the reason that electrospray ionization is used mostly for highly polar compounds. So it is best for polar non-volatile compounds. So this word is important, and because of this polarity, there is a possibility of forming multiple charges. There is a possibility of forming adduct ions. So this is quite likely because of that. Okay. Yeah. So we'll talk about advantages and disadvantages of ESI. Advantages is that the practical limit, though I said it is 70,000 Daltons, it can go even up to 150,000 Daltons. So very good sensitivity. I should say very high sensitivity. It can go even up to femtogram level now. It's a soft ionization, so you get only molecular weight. Easily adaptable to LC, so it is very good. Little matrix interference, so that's good. Easily adaptable to any mass spectrometer, so you can have quadrupole, ion trap, time of flight, any mass analyzer can be connected to this. Multiple charging, allowing analysis of high mass ions with relatively less M by Z instrument. So if I have a quadrupole which can go only up to 2000 Daltons, in case of LCMS it goes up to 2000 Daltons. But then if I have a compound which has got 10,000 molecular weight. Now looking at the molecular weight, we may say that this is not possible on this mass analyzer because molecular weight is 10,000. It will not come because this mass analyzer goes only up to 2000 Daltons. But suppose this 10,000 Dalton molecular weight can form 10 charges on that. That means what will happen? 10,000 by 10, that means it will appear at M by Z value of 1000. So if my molecular mass analyzer goes only up to 2000, this molecule which has a mass of 10,000 can be analyzed by this. So that is what it says, multiple charging, allowing analysis of high mass ions with a relatively less M by Z instrument like a quadrupole which can go only up to 2000 Daltons. Multiple charging giving better mass accuracy through averaging. Now it's again one advantage here, because multiple charges when they get formed, suppose there is a molecule which forms 5 charges on it. It also forms a 4 charges on it. It also forms a 3 charges on it. It also forms a 2 charges on it. And it also forms 1 charge on it. So for the same molecule, you will get 5 masses, because one is because of charge 1, one will be coming because of charge 2, charge 3, charge 4, charge 5. And all these 5 masses which you get, they will not be up to 4th decimal. They will be a unit mass resolution if we use quadrupole. Now, when you take average of all these 5 masses, you will come closer to the actual molecular weight of this compound. Okay, so that's the great advantage of this system, that you can get accurate mass. The disadvantage is low salt tolerance, which I already said. I cannot use phosphate buffers. Difficulty in cleaning when you have those kind of problems. Low tolerance for mixtures because it forms multiple charging and things like that. If you have not a single compound, you have mixtures, the multiple charging will confuse you. So that is what it says. Multiple charging may be confusing, and mixtures are there. It will give a complex kind of a mass spectra, which will be a disadvantage for you. This is summary of electrospray. Is an atmospheric pressure ion source. Smaller molecules may be singly charged. High molecular weight samples become multiply charged. They form especially polymers, and molecular weights up to 150,000 Daltons can be measured. So this is what we have already looked at. This is just a summary of that. We go to the, I will not talk about that because it is going to take time. So electrospray can be used for proteins, peptides, nucleic acids, a lot of pharmaceutical compounds, a lot of natural products. What is important is sample has to be highly polar, and then electrospray can be used very easily. We go to the next technique, which is called as atmospheric pressure chemical ionization, APCI. And this is used for semi-polar compounds. So we have seen ESI, which can be used for highly polar compounds. We are coming to APCI, which is used for semi-polar compounds. Now here, only consideration is that because it is semi-polar, could be thermally stable. So we can heat the compound up to 500 to 600 degrees centigrade without breaking it. And then we use the ionization, chemical ionization. That means the solvent itself, which is used for in a mobile phase, or the nitrogen gas, they help in ionization of the molecule of interest. Okay, so we require some kind of a matrix here also. Then compounds can be thermally they degrade because temperatures are high, and it's a brute force technique. We are using little higher force. How it works? So you have heated blocks here. Your sample is coming. It gets vaporized. It forms a spray, but then it gets vaporized here itself. And the vapors of your sample, pressure here, the vapors of sample come up. Now there is something called as a corona discharge needle, which is put here. Now to this needle, we apply a very high positive voltage to the tip of the pin here. This is corona needle, I said. So the needle has a very sharp edge here. So we apply a very high voltage onto this, and the voltage cannot be kept there or sustained there onto the tip. So it will flash. It will give a flash plasma corona discharge. It will give a high discharge, and that discharge has a high temperature, which will ionize the mobile phase molecules. And then these mobile phase molecules will ionize the sample molecule, and then sample gets MH plus, again a protonated sample will come, and it will get into the mass analyzer. And that is how it is called as chemical ionization, because it is similar to chemical ionization which we have seen earlier, where methane is used for chemical ionization. Here we use the mobile phase methanol or acetonitrile or whatever we use. That is being used for converting the molecule into ion. And that is why it is called as chemical ionization. So this is the same thing, APCI mechanism. Sample is vaporized, vapor passes over needle at high voltage, ionization of solvent occurs, solvent transfers charge onto the analyte, just the same as chemical ionization, and charge analyte enters into the mass analyzer. Okay. So this is what happens here. So you have the corona discharge here, and sample comes. The solvent molecules, you can see small solvent molecules are ionized. They transfer the charge to the larger sample molecules, and then sample molecules enter into the mass analyzer. Well, APCI, what are the important points? Multiply charged ions are rare because this is semi-polar molecules. It doesn't have so much of a capacity to take protons, maybe one or two groups only, so it doesn't form multiple protons, doesn't get attached to it. That is thing. So you do not get multiply charged ions. More tolerant to salts, but I don't consider it, because any mass analyzer, we should not use salts with it. Less adduct forms, because again it is semi-polar, it does not have that capacity to attract some other groups on it, so it doesn't form adducts. Used for smaller pharmaceutical compounds, steroids, lipids, etc. So it can be used for smaller compounds with molecular weight something like 1,000 or less than 1,000. Better with normal phase solvents than ESI. So to some extent we can use some normal phase solvents here. These are the pros and cons. It is very simple. Ionizes wide range of compounds, works better than electrospray for non-polar compounds such as lipids and steroids. So I will use that for semi-polar compounds. Disadvantages: needs high flow rate compared to electrospray because the solvent has to be used for the ionization. So you require to have sufficient solvent vapor around it. So you require to have higher flow rates. Compounds must be thermally stable as the everything gets heated to 500 degrees centigrade. So you require compounds to be stable and needs low volatile buffers always. Okay. We come to the last one, APPI, atmospheric pressure photoionization, and as the name says, the photons, the ultraviolet radiations photons will ionize some of the molecules. So that is called as photoionization, and that happens. So APPI is used for non-polar compounds. Okay, so generally it is used for non-polar compounds. The compounds which cannot get ionized by APCI, we try them by APPI. Okay, so this is how we can have two ways. Molecule, when it is bombarded with ultraviolet radiation, it can form M plus. If the molecule is soluble in a solvent which is protonic solvent like methanol, it can form MH plus. Otherwise, it will form plus. Not all the molecules will get ionized by photons directly. So we have another method which is called as dopant APPI. So what is done? The dopant molecule gets ionized first, which we are sure that it gets ionized. So we'll form a dopant ion. And this dopant ion interacts with the molecule to give MH plus or M plus, depending upon which is the solvent used for dissolution of your molecule. If it is protic solvent, it will give MH plus. If it is more non-polar solvent, it will give you M plus. And that is how dopant helps you to have the ionization. If it is not possible by direct ionization, dopant will be told, and it can get ionized, and it is generally introduced after the call, so that then it goes into the ionization chamber. This is how it is. This is the UV lamp. This is the LC element which comes like that, and because of the photons, ultraviolet photons which are bombarded onto the molecule gets ionized, enter into the mass analyzer, and there is a pump which will remove other solvents. Some of the molecules which get ionized by this is fluorothene, hydrocortisone, estrone, etc., which are non-polar molecules. So let us now compare all the techniques together. Okay. So we have EI, which can analyze a lot of non-polar compounds, molecular weight maximum 1000, generally 600 or 800. Total number of molecules with GC-MS with EI can analyze are, as I said, less than 10% of the overall number of molecules, organic molecules. Then we have FAB, which is outdated, which can go up to something like 5,000 or 7,000 Daltons. It can take a lot of polar samples. Okay. Outdated technique, but we have thermospray, which is also outdated, can go up to something like 2,000 Daltons or 1,000 Daltons roughly, and it can do semi-polar compounds. We have seen that. Then we have APCI, which is used for semi-polar compounds. Molecular weight range goes up to about 1,000. Then we have APPI, which can do analysis up to about 500 molecular weight, non-polar samples. And the last one is we have electrospray ionization, which can go up to 150,000 Daltons. Covers a lot of highly polar compounds, covers some of the semi-polar compounds, but cannot cover non-polar compounds. While APCI and APPI both can cover, or there is an overlap, and some of these semi-polar compounds can be covered by APPI, and some of the compounds which are possible to be covered by APCI, and both have got complements. So there are common probes which can do APCI, APPI. There could be common probes between ESI and APPI because there is an overlap. So there is a DWIS probe which can do both ESI and APCI. There is a DWIS probe which can do APCI and APPI together. Well, now you can see these three techniques which are here, which are called as atmospheric pressure ionization. All these techniques put together, we can analyze non-polar, semi-polar, and highly polar compounds at very low sensitivity. And of these three techniques, LCMS is possible now and atmospheric pressure ionization has made LCMS possible. So I thought of drawing the cartoon because I showed previously by the cartoon LCMS cannot exist because one is in water, one is in air phase, and the marriage is possible. Here, cock in the previous picture compromised. He said, I cannot marry fish, but I can marry duck because duck can exist in water as well as in atmosphere. And the marriage is successful. There is a chickling here, which doesn't chick chick, doesn't say quack quack, it says quack chick. And the marriage between the LC and MS is successful. So I thought of stopping the stage for 5 minutes and take some of your questions if they are, and have some break for somebody, and we'll again gather after 5 minutes. If that is okay with you, Kavita and friends, then we will stop at this time. We will break for 5 minutes and then proceed again for the rest of the things.
Yes,
So
sir. I think a 5 minutes.
I hope everybody agrees, and if any questions are there, you can put it. You can put it in writing and I will try to answer them. Or you can at least think about the questions and put them at the end of the thing. So we will have exactly 5 minutes. So we'll start exactly at 3:15. Okay?
Yes, sir. Sir, I think some of them have already have posted some of the questions. So Swapna will just get back to you in a minute with some of the questions, sir.
Yeah, no. Okay.
Hello, sir.
Yeah.
Sir,
Can you read?
can I take?
Oh yeah, please
Okay.
let me know what is
Sir,
it.
first question is, can a mass spectroscopy be used for the analysis of molecules like squalene and other larger organic molecules?
Yeah, it can be used. Uh, Squalene. Is it squalene?
Squalene, yes, sir.
No, no. Some of the molecules which are non-polar, they cannot be analyzed by mass spectrometry. Okay, so very non-polar molecule like hydrocarbons, the molecules like styrene, polystyrene, such molecules or polyvinyl chloride, and those kind of molecules are not possible by mass spectrometer. Even they have higher molecular weight. Because what is required now, unlike GCMS, where all the molecules below 1000 molecular weight are possible there because of the high energy of electrons, everything can get fragmented. Here, ionization is a soft ionization, and unless the molecule gets ionized, it is very, very difficult. So squalene, according to me, is difficult because of that. Okay, I have not seen any application with squalene, so I'm not. But it is mostly not. Squalene is not possible, though it has got high molecular weights. Phthalates are possible, okay, but squalene is difficult. Silanes are difficult. Squalene is difficult.
Okay. Sir, can I take second question?
Yeah, please.
Okay. Which solvents are commonly used for the most popular as a mobile phase in LCMS?
Yeah, generally we prefer methanol, water, acetonitrile. Combination of these three, along with the buffers, formic acid, ammonium formate, ammonium acetate, acetic acid. These are some of the common. Sometimes we use trichloric acid or etc. But then they are not very common. Okay, so depending upon the application, which we can use some of them. But then these three are common: water, acetonitrile, and methanol, and with buffers. Okay, so they are most common solvents. Yeah. Any
Sir,
other?
sir, we will take one
Yeah.
more question. How to
Yeah. Please.
optimize pH of the mobile phase in the LCMS?
Uh, Now, whatever conditions which are there for LC are also applicable here. Okay. So whatever pH is applicable for your column, generally column has a limitation. You said that it cannot go below 2 or below 3 pH, or it cannot go above 8 or above 9 pH. So you have to follow those conditions. Okay. So those are more. For MS, it is not that critical that you use pH which is tolerable by column. You can use the pH. Yes. Any other?
No, sir, rest we will take after the in the end of the session. Sir, you can continue
Because
with the yeah, your session, sir.
yeah.
Thank
Okay.
you, sir.
Now can I continue? 3:15.
Yes,
Yeah. It is
sir.
already 3:15.
Yes, sir. Yes,
Continue.
sir.
Okay. Fine. So we come to the mass analyzer now. We have completed ionization. So we have to get into the mass analyzer. And only now I will just put the same thing back again. And as you can see, as far as LCMS is concerned, if you remember my GCMS diagram, ionization was inside this compartment partially, because sample inlet part has to be in atmospheric pressure. But here the entire ionization device is outside the vacuum, because we are talking about atmospheric pressure ionization. So after the ionization happens in either ESI, APCI or APPI, ions enter into mass analyzer, they get into detector after separation, and then detector will sense the ions which are coming as they come out, and data system will plot them. And as I said, you require a very high vacuum so that the ions produced will be able to travel, because they are in vapor phase. They should be able to travel from this region to this region without any kind of a collision with any other gas molecules. So if there is a good vacuum, there will be a free path for the ions to travel from the mass analyzer to the detector, and that is why high vacuum is required. Okay. So let us go to the mass analyzer. I talked about quadrupole mass analyzer when we talked about GCMS, but again, as there are a lot of new entries today also, I need to talk about this mass analyzer in a little detail, because this is the one which is used for 90% plus applications. It will be a part of LCMS system, either in form of MSMS or in form of a hybrid mass analyzer. Also, you require a quadrupole. So quadrupole is one of the commonest mass analyzer which is used in LCMS as well as GCMS. And that is why we have to understand this mass analyzer in a better detail. Now this mass analyzer, as I've told the last time, this has got 4 rods. And these 4 rods, the lengthwise, they are only about less than length. So something like 25 centimeter in length to maximum 30 centimeter in length. Their diameter here is about 8 millimeter. Okay, so very compact, very small diameter tubes. And then there are 4 rods like that, and they can be held in hand. Okay, so 2 hands on 2 sides with the distance between them about 25 centimeter. You can hold your mass analyzer like that in your hand. So it is very compact mass analyzer compared to a magnetic sector kind of a mass analyzer, which requires a big room for installing that. Here the mass analyzer is smaller than the size of the LC. If it is single quad mass analyzer, LC will be more in size than mass analyzer. In case of GCMS, GC is bigger than the mass analyzer, MS part of it. Okay, so it's a very compact kind of a mass analyzer. How it works? So it has got a DC and RF voltage on that. That means I am applying both. DC means direct current, RF means radio frequency, that is alternate current. So both the voltages are applied onto this rod in such a way that at any moment, if these 2 rods are positive and these 2 rods are negative at that time, very next moment these 2 will become negative, and at that time these 2 will become positive, and the charge is rotating. And on that, so what we have RF voltage which is applied and a DC voltage which is applied in such a way that at a particular DC RF voltage, the ratio which is important, at a particular DC RF voltage, one ion gets stabilized and go to the detector. At that voltage, all other ions will go out. As this ion we are seeing going out, some other ion, if I would have put it also would have gone out. So at one DC RF voltage, only one ion goes to the detector. All other ions either discharge or they go out into the vacuum system. maybe at some other DCRF voltage, as I'm scanning this voltage, this ion which is shown by red color will get stabilized and go to the detector. But at that moment of time, this ion which is shown by green color will go out. Okay? So I can scan all the ions in a given range. Suppose if I have a quadrupole which is generally used for LC up to 2000 molecular weight. So I will be able to scan from 0 to 2000 all the masses as they travel from here to here by scanning the DCRF voltage, which can go from 0 to 2000. Generally, we never go from 0 because we have a mobile phase which will otherwise interfere a lot. So we generally go from 50 to 2000 so that we eliminate any masses below 50 which are may not be that important. So we allow all the other masses to go into the mass analyzer. Sometimes we can start from 30 and allow all of them to go. So generally the scanning range is say 50 to 2000 or 50 to 1000 or 50 to 500 or 50 to 700, depending upon what is the molecule which you are looking at. If all the sample molecules which you have do not have a mass above 500, we can keep the scanning range from say 50 to 600 or 50 to 700 on the safer side. So that is how the mass range is decided, and maximum mass which you can detect by quadrupole mass analyzer is 2000 dalton. So that is what or how it works. Now in a scanning mode, we continuously change the DCRF voltage and scan the mass analyzer in that given range. But when I want to analyze one particular ion continuously, I will use a DCRF voltage which is fixed. So at fixed DCRF voltage, only one ion will continuously go to the detector. All other ions will go out. So I will be able to measure, say, this ion continuously for the entire time. Okay, so I will never lose that ion. So when I use this in this particular mode, I will be able to detect maximum intensity of this ion and will be able to quantitate it better. If I do not do that, and if I want to measure this ion for a quantitative analysis at low level, I will not be able to do that if I scan it, because when I do the scanning, the turn of this ion in a given range comes only once. Because if you scan from particular range to particular range, and suppose this ion is a mass 420, 420 will come from 10 to 600, 420 will come only once. So it will only get a chance to get detected only once in this when it's scanning from 10 to 600. When I only do or I keep this DCRF voltage so that only 420 can go to the detector, I will never miss this ion. So all the time this ion will go to the detector and I will be able to measure the intensity of this ion to the maximum, and I can measure it at a very, very high sensitivity. So that is why there are two ways the quadrupole can be operated. One is called as a scan, other is called as a SIM. SIM could be single ion monitoring or selected ion monitoring. Scan means in a given range of a molecular weight, you can scan from low mass to high mass, okay? And you can get a mass spectra which can be used for qualitative analysis. Okay, so that is how the quadrupole mass analyzer works. I showed you last time that there is a DC, this is the AC voltage or RF voltage which is applied. This is DC voltage is applied in this direction, RF voltage is applied in this direction, and there is something called as a stability line. So this is stable region, this is unstable region. A is DC, Q is RF, and you get a line which is stability line, but this is not a good line, so you can change it. This is poor. If it is like this, no ion will be able to be seen. All the ions will get to the detector and you will not have separation at all. Here you will get poor resolution because all these ions will go at one time to the detector, and when you have this only part of the ion will go to the detector, or with the exact m by z will go to the detector. So if there is another m by z, it will go like this and come back like this. Another one, it will go like this, come back like this. So for different m by z, will cross this stability line, and when they come to the stability line, they get detected. When this ion comes here, it gets detected. And that is how the stability diagram is very important for quadrupole mass analyzer, and that will decide which ion will be detected by the detector. Now, if I use a single quadrupole as a detector, I will get only molecular ion, because I told you that the quadrupole, the electrospray ionization is a soft ionization technique. It does not give you fragments. So if I use this, I will get only molecular weight information. Now, can I use that information? Can I use a single quad for some analysis? I can do that, especially if I'm doing a synthesis work, organic synthesis, and if I'm mixing compound A and B and carrying out some reaction between A and B, and I'm getting a molecule C. Now, if I'm planning for that reaction, I definitely know what is the molecular weight of C. I want to see whether it is getting formed or not. I am sure if that is getting formed, I will get that molecular weight information in my mass spectra. So I only look for that kind of information. I can use LCMS alone and can get a molecular weight of the compound. Okay, so here I'm showing you two things. I'm showing you PD spectra of the molecule and the mass spectra of the molecule. So here I'm getting only molecular weight information. Here I'm getting a PDA spectra. Now PDA also can give you some kind of a structure information, but PDA is not a real identification tool, because you can see these two molecules here, this one and this one, they show almost identical spectra. This molecule and this molecule also show almost identical spectra, but their masses are different. This is 361, this is 226, this is 281, this is 279. So the molecules being different, their spectra looks identical. So PDA alone may not be able to have any usefulness, but the mass spectra will definitely be able to distinguish between these molecules. So LCMS alone can be used. So I have shown you that there could be question mark about the PDA spectra, while the mass spectra would be definitely able to give you a lot of information. Okay. Then I'm also going to talk about something which the mass spectra of today can be connected to ultra fast LCs also. Now here the entire separation of 3 plus 4, 7 compounds is done in a minute by using the ultra fast LC. That means the peak width of this peak is hardly not in second, it is in millisecond. So the mass spectrometer is able to detect this peak or not. If the scanning of a mass analyzer, as I said, I scan the mass analyzer from low mass to high mass. Now how fast I can scan it? Today's scanning speed of a mass analyzer is 30,000 Daltons per second. Now 30,000 Daltons per second means what? It can measure in 1 second. If I have a mass range of 0 to 1000, in 1 second I can measure 30 mass spectra. Now if this duration is 200 milliseconds between this peak start to peak end, so 200 milliseconds is 1/5 of that, and 30 mass spectra I can record in 1 second. That means in 200 milliseconds I can record 6 mass spectra on this peak. So even if peak is very fast, I'm able to detect many mass spectra. So if the mass spectra itself is very fast, you will be able to detect even a fast chromatogram which comes from ultra fast LCs. But if you have a poor scanning speed mass analyzer, it will not be able to detect so many peaks on the spectra. So today's mass analyzer are working at 30,000 Daltons per second. I remember when I started talking about mass spectrometry in 94 or 95, 1994-95, the quadrupole had a scanning speed of 4,000 Daltons per second. And now it is having the scanning speed of 30,000 Daltons per second. So that has made the change, and that is why it can be used with ultra-fast LC very easily. Okay, so you can use a single quad, and you can do a lot of work with a single quad. But then the problem is that you only get one single peak and you do not get fragments. And that's one drawback. I'm just showing you ESI, APCI, all the different modes of analysis. So the main problem GC with EI and LCMS with ESI, if we compare, we can say GCMS with EI has electron ionization. Here we have electrospray ionization. Ionization under vacuum, here it is atmospheric pressure, ESI. Gas phase ionization, here it is liquid phase ionization. Ions get formed in liquid phase itself. It is hard ionization, it is soft ionization. Hard ionization gives you a lot of fragments. Soft ionization only gives you molecular weight. Here, electron is ejected to form a positive ion. Proton is added or removed to give a positive or negative ion. I only talked about positive ion, but the acids or phenolic compounds can give you negative ions also. They can lose proton and can give negative ions also. So mass spectrometer is able to do both positive and negative ions. Okay. May or may not get a molecular ion. Here, molecular ion is difficult if the molecule is fragile in case of electron ionization. Here, because the ionization is soft, you always get molecular ion. Gives lots of fragments, usually does not give any fragments. Here you have a library searchable spectra. There is no library available for LCMS. GC-MSMS is not needed for fragmentation. LC-MSMS is used for fragmentation. We'll see what it is now. And for MRM transition, molecular ion is not usually precursor ion. For MRM transition, molecular ion is mostly a precursor ion. These two last points we will talk after we cover a few slides now. Okay, so this is the spectra which we get in case of GCMS. This is EIMS, electron ionization. Strong, hard ionization, you get fragments of this molecule. This is acetophenone, which we have seen. We saw the molecular weight, we saw this is base peak, everything we have seen. Now, this is a product ion spectra of acetophenone when we use the same compound in a LCMS. So we get 120, we get this. But again, this fragmentation is different than the fragmentation obtained here. Okay, so EI gives you many more fragments. LCMS, I did not get many fragments. Okay, I'm not going into that. I'm specifically coming to this molecule, which is called as salbutamol, which is a very, very polar molecule, very labile molecule. If you heat it, it will decompose. But in case of ESI, I got a very nice molecular ion because ESI is a soft ionization. It gives me only molecular ion with a proton added. So the actual molecular weight of this compound is 239. I am getting a peak at 240 because proton is added and I don't see anything here. So if this compound is unknown to me, I do not know that I have a salbutamol. And if I want to find out what is this molecule, I need to break it. So I need to break it in LCMS. I cannot break it in GCMS because this is a labile molecule, thermally labile molecule. So I require something else. So I'm not going into that. Let us look at the reasons for LCMSMS. Now GCMS is too hard, gives poor fragments with only lower masses if I use the GCMS for highly polar molecules. LCMS with ESI is a soft ionization, gives only molecular ion and no fragmentation as we have seen here. No fragmentation. And to have further fragments, we require MSMS, that is tandem mass spectrometry. So to get fragments in case of LCMS, we cannot just use LCMS, we have to use LCMSMS. So what is required for LCMSMS? This is what we require. We require a collision-induced dissociation cell. So we require 3 quadrupoles. So we require 1 quadrupole here. This is second quadrupole, and there will be another quadrupole. This second quadrupole is not called as a quadrupole. It is called as a collision-induced dissociation cell. Okay, so this cell does a job of fragmentation. So what we do in the first quadrupole, we select the ion which we want to fragment. So currently we have seen that 240 as the ion, or we can consider some other ion with mass say 420. So we have chosen a molecular ion with mass more 420, which has come from my quadrupole, which is operating in selected ion monitoring mode. So only 420 I have selected and it is allowed to come to the second quadrupole. Now, as I said, second quadrupole doesn't behave like a quadrupole. It is behaving like a collision-induced dissociation cell. What is done here? Once this ion comes here, I give a RF frequency to this quadrupole in such a way that this ion starts vibrating in this area quickly. Okay, this vibrates here. And then from the other side, I am putting a leak of argon gas. Now this argon gas collides with my molecule, which is coming here and vibrating, to which I call it as I've given a collision energy to it. And because of the collision energy given to it, and because of this collision with argon, it fragments. It gives me fragments which are called earlier, this ion used to be called as parent ion, and the fragmented ions were called as daughter ions. Now the names are changed. This ion is called as precursor ion, and the ions which get formed in the collision cell are called as product ions. And these product ions, which are formed here after collision, they get out, or they are driven out, they go to the next quadrupole, which will separate them, and I will get a product ion spectra or fragmented ion spectra, and that spectra will give me the information about this ion, because it has broken to give me those fragments, and those fragments will reveal the structure of this particular ion. So let us say that I have taken this 420 ion into here, it gets fragmented here, and the fragments of these ion go to the next quadrupole, which will reveal the structure of that particular ion. Okay, so what I have done, I have taken ये 420 को मैंने अंदर लिया CID सेल में, उसको दिया punches collision, and then it broke down because of the punches and revealed the information which I wanted, and then I analyze that information and come to the structure of this. That is what a CID cell does, and CID cell even otherwise does this job, and in mass spectrometry also CID cell is doing exactly the same job. So role of collision induced dissociation cell, it does the fragmentation through a CID, collision induced dissociation of a quasi-molecular ion by accelerating these ions into the cell, that is applying kinetic energy to the ions. We call it as a collision energy. It bombards with nitrogen or argon gas, and transmitting these fragments, once they get formed, they have to be sent to the next quadrupole. So from little higher pressure they are in the quadrupole, because we are putting the argon leak, they have to be sent to the low pressure under vacuum to the Q3 for analysis according to the mass to charge ratio. And then whatever spectra we get, we call it as a product ion spectra, that reveals us the structure information. There is something written here, you forget that at the moment, I am not going to talk about it and in the given time. So now this is the spectra of that salbutamol, which we have seen. 240 was the only peak which we are getting in the LCMS alone, but when we did MSMS on that, that means we have taken that 240 into the collision cell, given energy which is 25 volt, and because of that energy, the argon bombardment, this salbutamol has broken into pieces, and each piece has revealed me information that there is one water loss here, there is another C4H8 loss, that is this butyl group has lost. 148 is my major peak, so there is another water loss which has happened here, and then I'm getting this 148. So if I increase the collision energy, I may get some fragments on this side also, and that is how the spectra would be able to tell me more about this molecule, and I can find out the structure of this molecule with that. Okay, so this is how the product ion spectra, which can be obtained by using MSMS. Okay, so what MSMS can do? It can do wonderful things. It can do a full scan like a single quad. It can do single ion monitoring like a single quad. It can do a product ion scan to give you structural information, just now which I explained. It can do selected reaction monitoring, or SRM or MRM, which I'm going to explain to you now, because that is the one which is very useful in quantitative analysis. If I get time, I can get into precursor ion scan and neutral loss scan. Okay, so there are so many things which are possible in case of a quadrupole mass analyzer, triple quadrupole mass analyzer. Now we are talking about now MS. Okay, we don't talk about a single MS. So this is how it looks like. This is the ionization source, ESI. This is the first quadrupole. This is the second quadrupole. In case of our LC system, we do not have quadrupole here. We have octaplet quadrupole. So it is 8 plates which are put in terms of applying voltages. Argon gas is put inside, and it gives you much better results compared to just putting quadrupole here. And this is the third quadrupole. So fragmentation would happen here. Fragmented ions will go to third quadrupole. It will separate those product ions or fragmented ions. They will go to the detector, and you get a mass spectra, and which can reveal the structure. So ionization here, selection of ion here, formation of that ion here. The fragmented product ions are separated here and they are analyzed by detector here. So this is how the entire system works like. Okay. So when I take a full scan, what I do, I only require actually one quadrupole to do a full scan. So I use Q1 for that. And at that time, Q2 and Q3 I will not use. So ions will just go from here to here and to the detector. So I just record the ions, so I know what is present in my sample. So I know I have a molecular ion with 240 mass present here. If I want to do a quantitation of that, I only Q1 I will fix in SIM mode, that is only particular DCRF voltage. So that ion will go continuously. No, sorry, this is product ion spectra. So I select the ion, it goes into Q1. I have selected that, it will get fragmented. So Q2 is on, argon is admitted, it will collide with, I apply collision energy, product ions are formed. So these are all product ions and they will go to the detector and I will get a product ion spectra which will something like this, and it gives me the structure information of this ion which a mass 420. It has given a protonated ion of 421 and these are the product ions which are getting formed. Okay, so that is how I can get the structure information about this ion. SRM or MRM is very, very important in quantitation. What I'm doing, I'm taking the sample which is coming from the column. I put this in a SIM mode. That means only one ion of my interest because I'm using it for quantitation. I know what I want to analyze. I am selecting that ion. That ion comes here, gets fragmented. I know this ion very well. So I know which product ion it is going to form. So I put this Q3 only for that product ion and then I can detect that. So by this way, I am monitoring one reaction, that is this precursor ion gives me this product ion, and this reaction I am monitoring, one single reaction or one selected reaction I am monitoring, and that is why it is called as SRM. If I can use one after the other, many ions which will come here, many ions will get fragmented, and one by one, if I monitor several ions, one after the other, then it's multiple reaction monitoring. I'm not monitoring only one ion, I'm monitoring many ions. Now, what is the advantage of this? Let us look at that. Okay, so I'm trying to analyze a drug which is verapamil in plasma. Okay, so I will look at, we'll go to that, and I don't know whether I have something. No, sorry. Okay, I will explain here only. So what happens if I have a plasma and this drug's in the plasma? Now there is one possibility that there could be a molecule which has got exactly same mass as my verapamil. So both of them will come here. Okay, and if I have a single quadrupole, what will happen? If I have a single quadrupole, both of them will go to the detector, and then, hello? If I have a single quadrupole, both will go to the detector. So the impurity coming from the plasma as well as my drug will both go to the detector, and then I will have a wrong results. Or even if I have no drug present in the plasma, it is all consumed, still I may get something coming out of the plasma which has exactly same molecular weight of my drug. It will still go to the detector and I will have false positive. So to remove that problem, I take a verapamil, I fragment it, and then measure the one of the fragment from verapamil to the detector. So what will happen because of that? The things which are coming from plasma are eliminated, and only my drug I can measure continuously. And in this way, I can get better signal to noise ratio. As you can see, 100 femtogram of this can be measured in a plasma. So that is the advantage of the triple quad system, that you can do SRM or MRM and measure the concentration of ion. And this is only possible in a triple quad system. It is not possible in any other tandem mass spectrometer. There are so many tandem mass spectrometers. There could be QTOF, there could be IT-TOF, IT connected to TOF, quadrupole connected to TOF. So all these mass analyzers are possible, but then here nothing will happen. Those mass analyzer cannot do SRM, they cannot do MRM, and they cannot do good quantitation. Okay, I do not know whether I have to go back. Okay. Yeah. Now this is a ion trap mass analyzer, which is the one which is, now this also cannot do SRM or MRM, but this is a good mass analyzer which can do MSMS within the single trap. Okay, so that is what it can do, MSMS. Now, how it works, you take the ions inside, stabilize them in the field, and then release them one by one. Then you can again take number of ions, stabilize them in the field, select the ion which you want, all other ions are removed. So say, suppose I have selected this ion in the field, all other ions are removed. I apply the gas inside it. I give a vibration energy to this, or energy to this. So it will start vibrating, which we call as collision energy. And the argon gas will hit it and break it. Now I will get product ions of this ion, and I can analyze them, and they can be measured. After analysis of the product ions, if I feel that one of the product ion I want to break further, so I will again take ions inside, I will select this, break this, and after breaking that, I select this ion and fragment it and get third stage of MSMS. So it can do MS, 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 MS multiple times, and because of that, it helps you to find out structural information. But as it works in this way, what is the problem with this is that you cannot do SIM or MRM at all with this. So it is a very poor quantitative analysis tool. It is a very good qualitative analysis tool. So ion trap is good for that. There is another one which can be called as QTOF. Okay, so there is a quadrupole, there is a collision cell MSMS, and there is a TOF mass analyzer. Today I did not discuss TOF analyzer because that was discussed last time. So probably I did not do it. But then time of flight mass analyzer works in a way that you have the plate here, you take the ions inside, push them here, and then they come onto this side. So they have a various kinetic energy which is there. And because of their difference in kinetic energy, their velocities will be different. And because of that, the small ions will move fast, larger ions will move slow, and that is how they get separated in TOF. And the TOF gives you higher mass accuracy up to 4th decimal level, while quadrupole gives you low mass accuracy, which is called as unit mass accuracy. So you cannot measure the masses separately as you can measure by the TOF. Okay, so TOF can give you 4th decimal molecular weight, while quadrupole can give only unit mass resolution. That means if you have a molecular weight of carbon monoxide is according to us is 28, but really speaking it is not 28, it is 27 point something, because carbon is 12 but oxygen is not 16 but 15.99 something. So the accurate molecular weight of carbon monoxide will be 27.4 decimals you can measure by this, while nitrogen N2 will have molecular weight higher than 28, but for unit mass resolution we'll consider 28 is the molecular weight of nitrogen. So you cannot distinguish by using a unit mass resolution machine if there is a loss of N double bond N in a molecule, it will be considered as 28. If it is a loss of C double bond O group, it is still considered as 28. If there is a loss of CH2, it is still 28. But the TOF mass analyzer will be able to distinguish that. So that's the advantage of having QTOF. But the TOF again works in such a way that you cannot have a MRM transition or SRM transition. So again, it is not good for quantitation, but it is very good because it gives you high resolution. So first quadrupole is used for selecting the ion. It goes here and you get accurate mass of your original molecule. You take that molecule into collision cell now. Collision cell will start working. Fragment that molecular ion, and then it comes here, and the product ions of that will be separated, and you will get accurate mass of product ions, and that will give us a good structure and information. So you can use QTOF like that. This is a QTOF, and there is now this QTOF can be converted into a W-shaped TOF also. So this is a W-shaped TOF. So there are 1, 2, 3, 4 kind of reflections are there, and that gives you still better mass accuracy. It can the mass accuracy is generally defined in ppm. So quadrupole mass analyzer gives something like 100 ppm or more, while this can give you a mass resolution less than or around 1 ppm. The previous one can give up to 5 ppm. This can give close to about 2 or 3 ppm. So these mass analyzers give you better mass accuracy up to 4 decimal level. Well, as I said, there is something called as precursor ion scan and neutral loss scan. They are very useful in metabolite identification. Okay, so drug metabolites, once they get formed, whether in vivo or in vitro, whatever way you form drug metabolites, generally when you are doing research, you give it the drug to the animals, or use cell lines or liver cells or something like that, and make the metabolites. And metabolites are analyzed by several, detection is done by several techniques. And one of the technique here is using neutral loss scan and precursor ion scan. And that is where triple quad is very useful there. And after that, you also require a TOF-MS for getting the accurate molecular weight. And using all those information, you can find out the drug metabolites. And that is one of the research activity which is to be done in drug discovery. We call them as ADME, absorption, dispersion, metabolite formation, and excretion. And one of the step in drug discovery is metabolite identification and finding out whether the metabolite is toxic or non-toxic. So this is going to be very useful for that purpose. So metabolite research purpose, the precursor ion scan and neutral loss scan are very, very useful. This is how they are useful. So generally when metabolites are formed, these are the kind of metabolites which get formed in phase 1 metabolism. So there will be addition of molecular weight to the molecular weight of a drug, M plus 16, or here also it is M plus 16, here it is alkyl group attached, M plus 1, or add of H, a loss of alkyl. So it will be minus 15, alkyl group gets lost and 1 added, or it could be M plus 16, addition of oxygen, addition of 2. If the reduction happens, that means double bond gets converted to single bond. So such kind of mechanism happens in phase 1 metabolism. Phase 2 metabolism, the drug gets more and more polar, gets more and more soluble in water, and finally gets excreted out. But in between it forms all these kind of compounds, M plus 175, M plus 80, sulfate conjugation. Here it is glucuronic acid. Here it is methylation, then acetylation, and amino acid conjugation. So amino acid gets added, or there could be glutathione conjugation where the molecular weight can increase by quite a bit value, 306 minus X. So these kind of metabolites, when they get formed, they need to be analyzed, and there you use precursor and neutral loss scan. So unnecessarily, I do not know, the time is very less. It is worth actually talking about that, but I'm worried about the time part of it. Okay, so I can go back a little bit faster and look at this precursor ion scan. Okay, what is done in precursor ion scan, that all the molecules which are coming from your quadrupole, all are taken to Q1. Okay, all of them are fragmented, and after fragmentation, you select only one ion which is of your interest to come out. Now, I showed you the metabolites, how they get formed. Many metabolites have addition in the molecular weight. So M plus 16, M plus 14, M plus 180, all those kind of molecules get formed when metabolites of the drug gets formed. Then what will happen? All those metabolites which get formed, where the molecular weight has increased by some unit because of addition of some group to the drug, when it fragments, it will give a drug by itself out. So if my drug molecule has a molecular weight of 370, it will form all the molecules, many molecules with higher molecular weight because of the metabolite formation. When it gets fragmented, it will give me 350 as my original metabolites. So if I fix this at 350, I will be able to get those molecules in my sample, because I will be doing, say, in vivo metabolite studies. I have used a rat to which I have given a drug, and I'm monitoring the plasma for the metabolites, which is a very complex matrix. So what will happen if I do that? I'll get a spectra, I will get a chromatogram, something like this, which is a very complex mass spectrum. TIC. Now in this chromatogram, I do not know which is my metabolite. But when I do precursor ion scan for my drug, I know that I get this reduced to this, and I know these are my metabolites which are likely to be there. So then I analyze these compounds and I can analyze them for the structure of a metabolite. Okay, so precursor ion scan helps us in finding out the molecules which are of my interest. I can screen them. So this is called as a screening scan. So it will be able to find out the molecules. Okay, so this is used in very well in this one particular application. It is a veterinary sulfur drug analysis, and we have found out the neutral loss and precursor ion scan, both of them have been done here. We found out these are neutral loss of 173, we found out neutral loss of 109, we found out, and these are the peaks which are because of no, which one is that? Yeah, the green one is neutral loss. So this is a neutral loss, and pink one is precursor ion scan. So pink ones are pink precursor ion scan. So I can find out which are the drug molecules which are getting converted into metabolites, and these are my metabolites because they have got a neutral loss. What do we mean by neutral loss? If I have AB as a molecule, it fragments to give me AB as an ion. When it fragments, it gives me A plus as ion, and B becomes neutral. If I have another molecule which is CB, where C gets ionized, B is a neutral. If I have another molecule DB, where D gets ionized and B becomes a neutral. So when I have this B as a neutral, and if there are some other molecules present there where B is not there, but if I decided that I will just try to find out where B neutral is common, and I make a arrangement in such a way that my first quadrupole will scan the entire mass range, say 100 to 1000, then my collision cell will fragment everything, and my third quadrupole will scan with an offset which is expected neutral loss. So if neutral loss is say 44, which is generally happen when I have fatty acids, they will lose 44 as a neutral loss. Then wherever there is a fatty acid, I will see a peak because the third quadrupole has a scanning which is done with offset of 44. So it will not scan from 100 to 1000, it will scan from 56 to 956 because 44 is a neutral loss expected. So 100 minus 44 is 56, 1000 minus 44 is 956. So when I do that, I will get only those molecules which have fatty acids in them. So when I have some extract where fatty acids are supposed to be there, I can easily scan them by using a neutral loss scan like that. So this is the advantage of that. Okay, so I'm coming to advantage of MRM. So 800 MRM transitions are possible in per second in a quadrupole. So when I want to monitor many pesticides together in a given sample, and there are about more than 800 pesticides in a given and are known, and I do not know which pesticide is used by the farmer and which pesticide has contaminated my food. So I have to be very careful when I analyze any food matrix for the pesticide residue analysis. Now this is a challenge because this challenge has been put by all the countries, especially advanced countries like US and European countries, on the food which they get into their country. So they try to monitor these pesticides, and if the pesticides are above certain value, maximum residue limit which is set up by them, if pesticide is above that, the entire food which they have got into their country from the country who has exported, it all will be rejected. So the whole consignment of all the grains or all the mangoes or all the grapes which is going there will come back if the pesticides are on the higher side. So the labs in India, they have to monitor these pesticides for all the export products, especially food products which are going out of India. And there are so many pesticides they have listed. So we have to analyze all those pesticides which are listed, whether the farmer is using those pesticides or not. All those pesticides need to be analyzed, and that is the challenge for the people who are doing this analysis. And I'm not going into all this, but I'll just show you some spectra Now these are the pesticides. GCMS can analyze, GCMSMS can analyze some pesticide. LCMSMS also can analyze. So we can use even MSMS for GCMS, which generally is not preferred. But when I want to analyze pesticides in dirty, not the matrix like food, I need to have MSMS, because MSMS get rid of the background or the interferences, and that is why I use LCMSMS also for that. I will show you some information. Number of pesticides which are possible to be done by LC, number of pesticides which are possible to be done by GC, and these are the list. I'm not going to that. This is what MRM happens here. So let us again look at the MRM, what it does. So here I've selected one ion of a pesticide. It gets fragmented here. Out of these fragments, one ion, again, all the fragments enter here, but only one ion I measure, which is called as a product ion. So I'm measuring one transition, one precursor ion, one product ion. So for all 800 pesticides, each one will have one precursor ion, each will have one product ion. And I make a list and tell my instrument to monitor all these transitions one after the other. And the speed of this measurement is 800 MRMs per second. So it can monitor so many MRMs per second. So what I need now, I need to have some separation is GC. And I do not require a full separation, peak to peak separation with that resolution factor of 1.5. I don't require that. I require only a very, very small separation in GC, and the entire separation of all these ions is done by this MRM transition in my triple quad system. And then I will be able to get many ions measured. Again, here it is shown that now there are two ions, one coming from my sample, other coming from my chemical interference. Both have same mass, both of them get fragmented, but I select only one mass of my, which is coming from my sample, one product ion. The other interference give me different product ions. They don't go into mass analyzer, and that is how I get selectivity for my measurement. And this is what happens here. So I'm not going into that. I'm going to show you a spectra where I have analyzed 439 pesticides in less than 25 minutes. No LC will be able to do this. No GC will be able to do in 25 minutes 439 pesticides. I have another spectra where 836 pesticides are analyzed in less than 15 minutes. So this kind of analysis is possible because of MSMS, because of LCMS, and especially LCMSMS. That experiment which I have is 836 pesticides analyzed in 15 minutes by using LCMSMS technique. So this analysis is required now, and there are lots of food testing labs which have come. They do this kind of a job every day for all the export product. Now they must be doing it for mangoes. In month of January and February, they were doing it for grapes which are getting exported from India. There is basmati rice which has to be done. There are a lot of spices which are exported from India. So all these labs are engaged in doing this kind of work. Wherever there is export of any of the products, food products going out of this country, this needs to be done. Unless and until these are certified that they do not have pesticides up to this level or below this level, no product can go out of India. And even if it goes, and even if then when they test it there, and if they found that our testing is not good, they will only believe their method. And if they find that the pesticides are more than the required level, the entire consignment of grapes or mangoes will come back, and that will be too much of a loss for the person who has sent it. Not only that, it gives us a bad name and a reputation in the country that goes down, that they have a lot of products coming which are not good. They are not doing good quality control of that. So all these analysis has become very, very important. There are lots of such labs coming up in India. They are already there. And as FSSAI is putting a lot of fundings for these kind of food testing, a lot of labs will be coming. And the people who are working in the analytical chemistry area, they have to get equipped with all these kind of techniques which are available for analysis of food, analysis of drugs in plasma, because again, we are getting a lot of drugs which are biopharmaceuticals. So the analysis is going to be different for them. We are getting more and more challenges by having the disease like corona, which is yet we do not have a solution for that. And that solution, even if we get any kind of a solution for that, that needs to be tested for its toxicity, and that those studies need to be done. Clinical trials have to be done. For that again we will require LCMSMS. So all these applications which are very essential to be done by technique like MSMS, either it is GCMSMS or LCMSMS. As again I am giving you this information that LCMSMS is more preferred because 90% of the organic compounds can be only analyzed by LC and then by LCMSMS. There are only 10% compounds which can be analyzed by GC and GCMSMS. So LCMSMS is becoming more popular because of that reason, and it only requires that the compound has to be dissolved. I hope you remember my 3 punchlines, that if you can evaporate, GC can separate. If you can dissolve, LC can resolve, that is LC. And if you ask mass analyzer what it can do, if you can ionize, it can do recognize, or it can do analysis of such kind of complex samples. So for mass analyzer, you only need to dissolve the sample in something, and pesticides, those can be analyzed by GC, can also be analyzed by LC because those are definitely soluble in some kind of a solvent. So there are a lot of overlap which are possible by doing LCMS rather than by GCMS. So LCMS is becoming more popular because of that. And because of this MRM, now we don't require good separation in GC or LC. MRM by itself does, the mass analyzer by itself does this separation, because these transitions are very specific to a particular compound. If there are 800 pesticides, for all those 800 pesticides, each one has its own MRM transition. Each one has its own precursor ion. Each one has its own product ion. Once you make the table for that, all those pesticides, you have to just feed that information to your software, and the software will do all this analysis for so many pesticides. Only you need to know when you put it on your LC, in which time window your pesticide is coming. So if in one time window, in this 25 minutes, there will be some 10 pesticides coming. The next time window, there are another 15 pesticides coming. Next time window, you are another 15 pesticides coming. So you should set your MRM according to the time at which they are going to get eluted. It doesn't matter if they are co-eluting partially. You need to only know that they are coming in this window. Now, if you have a window of something like 2 minutes, and in 2 minutes, 25, 30 pesticides are coming, it doesn't matter. They will be able to get separated because of these MRM transitions. So that's the advantage of, a great advantage of this MRM analysis, and which is only possible on a triple quad. Remember this, that it is only possible on a triple quad, and that is why quadruple mass analyzer, especially triple quadruple mass analyzer, is the most used system in the world. Okay, it can do a lot of things. I'm completing to the closure. I want to just tell you some of the things which are possible by LCMS. Drug discovery, finding out the structure of a particular compound. Metabolism, which I already talked about. Drug metabolites, ADME, so that is required. Toxicology, quantitation and toxic compounds which come. Pharmacokinetics, for which BAB studies, contract research organizations, they do this kind of job. Even in pharmaceutical industry, they carry out this. They have some preclinical studies they do within their premises itself. If they have animal house, formulation, structure and degradation products during or after formulation. QC, production, you use it for quantitation and identification of impurities. Unexpected peak, if you start suddenly getting, you need to find out what that peak is. You have to find out the structure of that compound. Contract research organization, I already talked about. Preclinical, clinical trials. Probably some of you know Accutest, or some of you probably been knowing about Lambda Therapeutics. They have, each one of them have more than 40 LC-MSMS system. Each system must be at least about 2 crore of rupees. So you can imagine how much investment they have done in the contract research organizations like Accutest or Lambda Therapeutic or Vida, and there are many more. Generic drug companies, they use it for QC and production. Protein characterization, molecular weight and 3D structure of protein. Proteomics, rapid peptide sequencing, post-translational modification, glycosylation, phosphorylation sites on the protein can be found out by MSMS. Confirm sequence and impurities, especially when we talk about enzymes, when we talk about biopharmaceuticals, you have to do this kind of quality control for biopharmaceutical, finding out the sequence and impurities in the new drugs which are coming up with protein-based drugs. Okay. Nucleotides, molecular weight and sequence in nucleotides, carbohydrates, molecular weight and sequence of carbohydrates. Proteins, as I said, they are what they are, you know very well probably. General techniques which are used as 2DG electrophoresis, 2D gel electrophoresis, capillary LC, mass spectrometry, bioinformatics. These are the way generally they are done. You have a complex protein samples, you do separation on 2D gel electrophoresis and do the spot cutting on the gel, digest it with any kind of enzyme, do cleanup, and then do MAMDI top on that. So whatever information you get for all those proteins, you send it to database. Another way, same complex protein sample, you digest directly with enzyme. So convert protein into peptides, because the quadrupole kind of a mass analyzer or even time of flight mass analyzer cannot go to very high molecular weight compounds. So you do capillary LC and use LCMS, do the peptide separation which are after digestion, and again all that information send it to database. This will be such a complex information that you require bioinformatics tool to analyze all this information. Manually, it's just impossible to characterize the proteins like that. So this is the kind of establishment you require to do the analysis of very complex proteins. It is also used in agrochemicals, compound discovery, metabolism, like pest control kind of a thing, different pesticides, fungicides, herbicides which are required. Okay. Then it can be used for organometallics, structure, detergents, polymer analysis, environmental, identification and quantification of pollutants, pesticides, antibiotics in water, which is necessary, especially fish ponds, where the you have to use when you fish are produced in a large scale in a farm, to take care of those fish, the health of those fish, you add some antibiotics in them in the water, and then those antibiotics can get into the fish. And if fish has antibiotics inside, if you eat that fish, you will have antibiotics accumulated in your body, and your immunity will collapse because of that. So that is why you need to analyze them. Food, chemical contaminants, antibiotics in food, natural toxins need to be studied, toxins, etc. Animal feed, we are not worried about the quality of food ourselves we are taking, forget about animal feed. Scene of crime, illegal substances, toxic agents, horse race doping, we don't leave even horses, feed them with drugs, explosives, drugs of abuse, neonatal screening, that is one important thing for which LCMS is used. There is inborn error of metabolism or newborn screening, where LCMS and GCMS are used, and find out the metabolic disorders in newborn babies, and then if there are some disorders found, those can be corrected at early age. And generally these what we call as newborn screening is generally done when the baby is only 3 to 5 days old. Is either blood sample or urine sample is analyzed to find out metabolic disorders, and if disorders are there, some enzymes can cure them and they can be better as they grow. Otherwise, some of them could be fatal, or they will develop with some disabilities, and that's very bad for the parents. Then LCMS in academia, related to all the above, fundamental research, teaching, which I am trying to do. Well, I would like to stop here. And any questions you have, I'm there to answer those questions. Okay, so thank you, Kavita, and
Yes, sir.
all of you, and thanks all for their presence, and hope they have liked it. The break probably would have helped them, because that could have removed some kind of laziness which lunch session. Okay, so
Yes,
Yes,
sir.
sir.
yeah, any questions? I will reduce this and I will be ready to answer any questions.
Sir,
Yes, sir.
Yeah,
My colleague
sir, can I?
Swapna will be taking questions. Yes.
yeah,
Yes,
yeah. We are
Swapna.
getting the questions. Okay.
Okay, ma'am. Sir, I will take questions now.
Yeah, yeah, please.
First question, sir. How is LTQ orbit trap LCMS technique is different or better than HPLC MSMS?
Okay, good. Okay. Now, orbit trap is a special. Hello. Yeah, orbit trap is a
Yes,
spatial
sir.
mass analyzer which has also very high resolution. Okay, so it is similar to ion trap, but ion trap doesn't have a high resolution. Well, orbit trap has a very high resolution. It is even much better than a time of flight mass analyzer. So advantage is that whatever measurement you are doing on orbit trap, you will get the molecular weights even less than 1 ppm mass accuracy. So the molecular weights would be available up to something like a fifth decimal level. Now, what is the advantage of that? Now, let us say if I say my compound has a molecular weight close to 340, either it is 340 point something, I do not know how much it is, but it is 340 point something. Now, if I look at all the molecules of mass 340, there could be at least about 300 molecules with mass 340. Okay. But when I say I have a molecule which has got a mass of 340.2578, now I'm very specific. The molecular weight is 2578. And if I say my mass analyzer, if I use the time of flight, it has a 10 ppm mass accuracy. Not very good. 10 ppm is still better than quadrupole, but it is not so good. So then after that, I will get a mass and I say the mass accuracy is within 10 ppm. So it will list compounds which could be 40, which have got a mass of that particular mass which I talked about. Okay, so still there will be 340 masses. Then when I say I have a mass analyzer which goes below 5 ppm, then probably from 40 I will come to 10. When I say I have got something below 3 ppm, so from 10 I will come to 3 masses which are very close to that. And when I come to less than 1 ppm, probably I will come to the compound which is my compound. Okay, so that is how orbit trap helps. So when you have a very complex proteins and very large different samples, and you have to identify your compound very specifically, this high mass accuracy helps a lot. Now, how this accuracy is calculated? Whatever mass you measure and whatever mass is actually there. Suppose you have a standard with known mass, and if I use an accurate mass analyzer, and it gives me some mass which is having a variation at the fourth decimal level. Okay, so 0.0007. So that is the difference which I got between my molecular weight and the molecular weight which is standard calculated by using the atomic weights. So this mass difference delta M divided by the molecular weight 340 into 10 raised to 6 will be the ppm. That is how the ppm calculation is done. So you can calculate that on the basis of this, what is the mass difference which is expected. So it is expected to be less than 1 ppm. That means I'm talking at the level of fifth decimal level. And when I get such a kind of a mass accuracy, I come very close to the molecule, or I can pinpoint this is my molecule. And that is what orbit trap can do. Okay, so that's the main difference between normal LCMS and orbit trap LCMS. QTOF comes closer to that, but it is 5 ppm, and this goes below 1 ppm. And as I said, with 5 ppm, there could be still about 15 compounds or 20 compounds, which one of them could be my compound. So it becomes very difficult then. Yeah. Are you getting me what I'm saying? It's very difficult to explain in 2 hours of a lecture. I
Okay, yes, sir.
college in bioanalytical sciences, bioanalytical chemistry, where I take 70 lectures on mass spectrometry.
Yes, sir.
Okay, so those many number of lectures are required to cover the entire topic. Sorry, yeah. If
Yes, sir.
I have not
Sir,
covered or I
there
have
is,
not answered your question. Yeah,
sir, there is one more interesting question. What
yeah,
is
please.
the impact of GCMS,
Hmm,
LCMS in
hmm.
crystal pharmacology in drug development?
Yeah, okay. Now, as I said, generally most of the drugs are non-volatile, or they are thermally labile. So LCMS is definitely a tool which is more preferred in a pharmaceutical industry. GCMS has few applications, especially when we talk about volatiles or headspace or residual solvent analysis. Okay, so GCMS is also useful for finding out some of the genotoxic impurities. Now, that is a new field which is coming up in pharma quality control area, and recently there are nitrosamines which are very highly carcinogenic compounds, and they are found in some of the drugs like Satan, and these have to be analyzed at very low level, and that is what is possible by out of 7 or 8 nitrosamines, 6 or 7 are only possible by GCMS. So you have no other alternative to buy a GC-MSMS, because you require that MSMS for that specificity, because it can do that MRM transition. So GC-MSMS is being used for two purposes in pharmaceutical industry. One is for this kind of genotoxic impurities, because many of them are volatile in nature. Then there is another area which is called as extractable and leachable area. So when packings are used, the impurities from packaging material like phthalates or bisphenol A and those kind of things which are poisonous, they can enter into the drug, sip from the packaging into the formulations, etc. So those need to be analyzed, and many of them also then analyzed by GCMSMS. So GCMS, earlier days, few years back, probably GCMS was hardly used in pharma industry, but now because of these genotoxic impurities and extractable leachables, it is also preferred for that work. But when you talk about drug discovery, when you are talking about new molecules, and many of those new molecules, you require the structure measurement or elucidation of structure, and you require definitely a high resolution LCMS system or NMR, and combination of these two techniques would be definitely required, and that is what is used. Did I answer your question? Can you just
Yes, sir.
put your mic on and say yes?
Ye-
I do not know who has asked this question, but just make sure that this is the question
Oh,
which I understood and explained.
uh, yes, sir.
Yeah.
Sir, that I think participant is not online. So, sir,
Oh, they are
can I
not
ask?
on.
Sir, I'll take next question, sir.
Yeah, please.
Sir, how to differentiate GCMS data and LCMS data? One of the participant is asked.
Yeah, no. When you get a data on any of the computer, now today's data system, it would clearly identify from where it is coming. Okay, so it will say it is a EIMS spectra or a GCMS spectra. So you know already, looking at the data somewhere on the corner, somewhere in the whole report, it will have a mention of that. Okay, so it will mention that it is from GCMS or it is from LCMS, or at least it will say EIMS. So you know that it is electron ionization, that means it is GCMS. Or it will say it is a ESI MSMS spectra. So you know it is electrospray ionization. Or it will say APCI MS or APCI MSMS spectra. So when you get that information, you know coming from either GCMS or LCMS. Okay, so most of the time the report will come with clear demarcation that it is from this, or otherwise whatever is written on the top of the spectra somewhere that it is ESIMS or EIMS, that will tell you that it is a LCMS or GCMS spectra. Yes. Anything
Sir,
else?
yes, sir, we will take two more questions.
Yeah,
Is it
please, no
okay?
problem.
Yeah. Sir, can ESI leads to adduct formation?
ESI has a good chance of adduct formation. When you have a ESI spectra taken for any molecule, there is a good chance of adduct formation. It can form adduct with sodium, it can form adduct with water, it can form adduct with potassium. These are the elements which come because of the glass itself, because there is a sodium in the glass, so it can, or sodium in the detergent. So if you have washed your vessels, glass vessels with detergent containing sodium, sodium remains back, and if you add your mobile phase or your solvent in that and use that solvent for liquid extraction of a drug, that sodium will be there in that, and sodium will compete proton more strongly, and sodium adduct will definitely get formed. So adduct formation is very common in electrospray ionization.
Okay. Sir, if
Yeah.
there is if
Huh.
there is positive ESI and
Hmm.
negative ESI in the
Yeah.
result,
Hmm.
which one we have to consider?
Yeah, okay. Now, whenever you get a positive ion ESI or positive ESI, you get a molecular weight increase by 1 unit. And when you get a negative ESI, you get a molecular weight decrease by 1 unit. So, you have the information then about molecular weight, because average of that two will be your molecular weight. That's okay. But then when you are, the question, I take it in the other way. I now when you have to do MSMS, which one needs to be used? Whether you have to take ESI, MS molecular ion to do the fragmentation, or whether you have to do ESI negative for doing the fragmentation. Okay, so that could be one possibility.
Yes,
And there
sir.
could be another possibility, if I want to do a quantitation, whether I should take ESI positive ion or ESI negative ion for MRM transitions. So
Okay.
all that depends upon the product ions which you get. If it is for structural elucidation, you can use both, okay,
Okay,
to
sir.
get additional information. But when it is MRM study and you want to do quantitation, it all depends upon what kind of product ions you are getting, and then which one is giving you better sensitivity, and by which one you can go down in the detection limits. So by optimizing your MRM, you can decide which one is giving you better sensitivity, and then use either ESI positive or ESI negative.
Okay, sir. Okay, sir.
Yeah.
Sir, there are many students who are studying LCMS and GCMS. So,
Yeah.
can you suggest any reference book so that
Oh,
students can refer?
yeah, I have some list somewhere, but what I can do is, if they can leave their email IDs, or if you have something which can be looked by them very commonly on the your internet or somewhere, I can put it.
Okay,
I
sir.
Yeah. Otherwise, I have to go back and search on my computer and get the list if they
Acha,
want.
sir.
Yeah, but
Okay.
take 5 minutes to 7 minutes at least. I don't know when I will get that.
No,
It is somewhere
yes,
on the computer on this same laptop, but I have to search it.
sir, it's okay. You can share that afterwards through the email with us.
Yeah, I can. I can definitely share the list, and whatever they want, any other question they have in mind, or it comes to their mind as they go out and think about whatever has been done today. If they have any question, they can come back to me and ask me the question.
Yes, sir. We have actually so many questions, but due to time a constraint,
Mhm.
we will note down all the questions and we will share with you. Once we
Yeah, please.
will get back to you and we will get all the answers, we will share all the answers with the participants also.
Yeah, yeah,
Uh,
please, please.
with this, I request Mrs. Anandi Rebella to give a vote of thanks.
Yeah,
Thank you,
okay.
sir.
Yeah, thank you so much, Swapna. That was very wonderful session of question and answer round. Good afternoon to everyone. I would like to take this opportunity to thank you, Data sir. Thank you so much, Data sir, for giving
Pleasure.
and and
It's a
explaining so
pleasure.
difficult topic in very simple and interesting way. I'm sure those who all have attended your seminar for day before yesterday and today now have very clear and in detail information and knowledge on GC and LCMS, sir. I'm
Thank
sure
you.
all have absorbed your 5S given by you, that is sensitivity, selectivity, separation, structure, and speed. And of course, how to eliminate sampling errors and background noise, sir. Sir, we are very lucky to have you as a speaker. Thank you so much, sir.
My
Secondly,
pleasure.
I'm thank you for our principal, sir, GN Khalsa College, for allowing us to conduct online webinar in lockdown period, plus all the HODs of GNID and other colleges, plus my HOD FIC Dr. Kavita ma'am and my colleagues, all the colleagues, and dear students from different location areas out of Mumbai and out of Maharashtra. Thank you so much, all of you, for attending and giving participation in these seminars, webinars. Thank you so much. And of course, big thank you for IT and admin team, which is run by Miss
Mr. Eldrin and Ashish. Thank you so much for your continuous technical support. Thank you so much to all.
Yes, thank you all. Take care of yourself.
Yes, sir. Thank you very much, sir.
Okay, I take